Okay, so here's a quick look at the supplementary notes that I prepared for you. This is going to be available for you to download, so you can go over those things yourself. I'm going to just quickly go over the content of this, plus we're going to solve an interesting problem in an interesting way. All right, so a quick overlook of that. 3 rules for the operational amplifier. Rule number 1, no current flows in and out of any of the inputs. So no current flows in and out here, no current flows in and out here when it comes to dealing with all the additional circuitry that is going to be surrounding it, the operational amplifier. Now, the rule number 2, the non-inverting input equals the inverting input voltage. So the voltage here is going to be always equal to the voltage here. Always, quote unquote, because there is that but. Okay, so always, this voltage equals to this voltage. So if this voltage is hardwired to certain type of a battery, and this battery is 1.5 volts, then automatically this here is going to be 1.5 volts. Okay? It's just the way it is within the operational amplifier. And where is the but? The but is, if calculated voltage exceeds the power supply voltage, then this rule no longer applies. And we have gone over that during our lecture. It was online. I showed you that on the multisim with the oscilloscope. So, if we have a certain type of a gain accomplished by dress up of this operational amplifier, and the gain is, well, let's say 2. All right. So we have plus 15 and minus 15 supply voltage. The gain is 2. And we have accomplished that by choosing the proper values of the resistors that were connected here and there and everywhere. So the gain is 2. And let's say we have 10 volts on inverting input here. We have 10 volts. Times the gain of 2 is going to give us negative 20 volts. Negative 20 volts is the calculated output, and negative 20 volts exceeds the negative power supply. If the calculated voltage exceeds that, then these are not going to be, they will be no longer equal in voltage. It's just the way it is. Okay? I love saying that. Now also remember, don't forget, power supply rails are not always drawn on the diagrams. I have drawn the power supply rails. Here's the positive power supply rail. Here's the negative power supply rail. On the schematic diagrams, most of the time, you will see that not being drawn. But it's always assumed, and yes, it is okay to assume, but it's always assumed that the circuits are powered, because that's the only way things are going to work. Right? So just to make things more clear visually, quite often those power supply rails are being skipped when drawing the schematics, and I'm repeating myself, but it's always assumed that the power is connected. So when you're assembling the circuit on the breadboard, yes, you have to connect the power. All right, ideal op-amp characteristics quickly. Input impedance. Impedance between here and the ground is going to be infinite. This input as well as that input. Infinite. This is the ideal. All right. Output impedance ideally would be 0, but it is not. For the sake of calculations, yes. For the sake of reality, you're going to have to find it out. Open loop gain is always infinite. Open loop gain, that means open loop. There's no any feedback loops between output and any of the inputs. There's no connections through any resistors or wires. It's just the way it is. So we call it open loop gain that this amplifier is going to give you, and it's infinite, which means that any slight variations between those potentials, things are going to go either north or south, right? So if the potential, if the voltage between here and ground is slightly higher than the potential between here and ground, then this whole thing is going to go all the way up. Not really, but let's just say all the way up. If, on the other hand, if this potential is slightly higher than that potential with reference to the ground, then it is going to acknowledge this inverting input and it's going to go south all the way. Is it going to go all the way? In reality, no, because it's limited by, things are limited by the internal circuitry of this operational amplifier, and you just have to find out what is the maximum voltage swing or the maximum output voltage swing, and you can find that on the data sheets, or if you happen to have the breadboard and the operational amplifier, you can connect things and you can check what it is. So for LM741, the higher limit of the voltage swing is going to be about 14 volts with the power supply at 15, about 1 volt less either way. That's as far as I remember from the data sheets of LM741. There's some other ones, and you have to find that out. What the maximum voltage, that's why we have the data sheet, what the maximum voltage swing is, right? So this basically here is what I just explained. You can read that once you download it. All right, what's the, how do we know what the voltage is going to be on the output with respect of the voltage on the input? Well, it's going to be the input voltage times the gain is going to give you the output voltage. For the most part. Okay. The last example that I have is going to kind of take things a little bit sideways, but that is also going, what I'm going to show you is tremendously going to help you with the calculations for lab 2, for the preparations, and choosing the proper values of the resistors. All right, so the gain of the inverting op-amp circuit. Here's the inverting op-amp circuit. Why do we call it inverting? It's because the input signal is connected to the input, which is inverting. So we have an inverting op-amp circuit. Now, in order to make things stable, because if there's no dress up, any slight variation with the infinite gain is going to go either this way or that way. Not a very stable circuit. We want things to be predictable and useful, so we dress things up with resistors. The gain of this configuration is as such. RF, this is the feedback resistor. It's giving the feedback from the output to the input. The feedback resistor value over the input resistant value, RF over Rin, is going to give us the gain. Do not forget that there's that negative sign here because we're connected to the inverting input. So let's say here we have the resistors 20 kilo, 10 kilo. 20 divided by 10 equals 2. So the gain is 2. Right? And with 1 volt on the input here times the gain, it's going to give us 2 with the negative sign. So we're going to have minus 2 volts on the output with a gain of 2, or minus 2 actually. Right? Now, non-inverting op-amp, the input connects to the signal, connects to the non-inverting input. And here is the feedback that goes to the inverting input. And here's RF, feedback resistor, and the input resistor, RF over Rin, and here's the input signal coming in there. The gain equals to, there's no negative signs anymore because signal is connected to the non-inverting input, so no negatives here, as opposed to here. So the gain is equal to, here's the formula, 1 plus RF divided by Rin, and that's going to give us the gain. The gain helps us with calculating the output. If there is gain, if the calculated gain is going to be 2, then 1 volt times the gain of 2 gives us 2 with no negative signs. It's just positive 2 because non-inverting input, right? Okay. Summing amplifier. Notice that if you remove all those two, this resistor and that resistor, it is basically this configuration right here, inverting amplifier. But if we have those resistors in parallel, and if you make those the same value, so if you have 10 kilo, 10 kilo, 10 kilo, then whatever the feedback resistor is going to be, if you want to make a true addition, then all the resistors are going to be the same, right? Because this divided by that is going to give you the gain of 1, plus this, the gain of 1. So if you have 1 volt plus 1 volt plus 1 volt here, the gain 1, so you're going to have 3 volts on the output. Because we're going by the currents, so the feedback current, this one here, equals to this current plus that current plus that current, which equals to, well, current equals voltage over resistance, Ohm's law. So this here is just taken apart a little further. So current equals voltage, so this voltage plus this voltage here divided by this resistance, plus this voltage here divided by this resistance, which is the same. It should be if you want to make a true adder, but you can change. It's going to have change the values, but you're going to have different results. Right? But if we have the gain of 2, then we're going to have the sum. So if you have 20 kilo and these 10, 10, 10, then the output is going to be the sum of these voltages times 2. Or if you have all of them 10 kilo ohms, 10 kilo by 10 kilo is 1, so you have unity gain. So this voltage plus that voltage plus that voltage is going to give you that voltage on that. And trust me, if you do the all the calculations, just remember it's going to give you the negative value. Because we are connected to the inverting input. Never forget the inverting here. Okay, let's analyze this circuit. We have an op-amp in a configuration of inverting amplifier. So the feedback is 20 kilo divided by 10 kilo. The gain is this over that. That gives us 2. So 2 times 2 should give us negative 4 volts, right? Well, let's multi-sim that. I already have that. What do we have on the output here? Well, we have 995.5 millivolts, so basically 1 volt, negative 1 volt. And did we just calculate the gain? 20 over 10. You must know there's 2 volts. 2 times 2 should be. Well, we forgot that there is offset here on this, and that makes a big difference. Okay. Bring things on the nice full page. All right, so we have this here now. Did you notice that? All right. Things are going to change drastically when we apply something different here. Now, rule number 1, no current flows in or out. And remember the impedance between those two themselves and the ground should be infinite, so there's not going to be any current flowing between here and here, because, well, nothing goes in, nothing goes out. But rule number 2 this voltage here is equal to this voltage, and since we know exactly what this voltage is because it's hardwired to 1 volt, then automatically we're going to have 1 volt here. So we can redraw this circuit as such. Yeah, let's make that disappear. Okay. So now we have current going this way or the other way, but there's only one current pathway. So we have a series combination of resistors. We have 2 resistors connected in series configuration. So this current, if we know what this current is, we will know what this current is, and since we have the values, we can tell what the voltage is going to be on this thing here. Then we can do some calculations and we can find out what the voltage on the output is. Okay. All right. So what we're going to, well, I'm going to find out first. First, we're going to find out the voltage across this resistor because it's going to be easy for us to figure out since we have 1 volt here and we have 2 volts here, the difference between the 2 volts and 1 volt here. Of course, that is 1 volt. The voltage across this resistor is 1 volt. Oh, come on. From here to here, 1 volt. With the plus and minus, this is the more positive side, this is the more negative side, so the current flows that way, as the arrow shows. If this voltage is greater than that voltage, because that can change, then of course the current is going to go that way. Always have to consider the direction of the current, because that is going to show you the pluses and minuses on the devices, especially this one here. All right. So now we established that the current flows this way because this is the more positive side of the resistor. So the current flows this way. So it is going to continue flowing that way. All right. What is the current value? We don't know what this one is, but if we know what this one is, of course, in series, then this one's going to be the same, right? All right, so voltage across the resistor times the resistor's value, divided by the resistor's value. So I equals V over R. So we have, what do we have? The V are in. That's 1 volt divided by 10 kilo. Well, let's grab a calculator. All right, 1 volt divided by 10 kilo. 10, 1, 2, 3. Okay, 10 kilo. That gives us 2, 3, 4, 5, 6. That's 100 microamps. But we're just going to do it 1, 2, 3 zeros and 1. Okay, we're just going to do this in the raw form. 0.123 amp. Just in the raw form, the way the number was born. Okay. All right. So now we know this voltage, and here, and we know this current. The voltage across this resistor we only calculated so we could find out what the current across through the resistor is. So that means the same current is through this resistor. And since we know what the current through this resistor is, and we know the value of the resistor, current, value of the resistor, multiply them two, and you're going to get the voltage across the resistor. All right, so we already have the number. Was the value of this resistor 20 kilo? So let's multiply that, because there's a multiplication sign here. Times 20 kilo, 1, 2, 3. That equals 2. So the value, the voltage of the resistor across the resistor is 2 volts. And that's the absolute value. We don't know, let's just establish where the pluses and the minuses are. Right? Since the current is flowing from here to there, so this is going to be the more positive side of the resistor, and this is going to be the more negative side of the resistor. So this here is 2 volts less than this point here. And what is this point? Oh, this point is 1 volt. So 1 volt minus 2 volts is going to give us 1 volt minus 2 volts is going to give us minus 1 volt. All right. Hey, cool. So let's take a look at the multisim to confirm that. All right. Now, quickly, what do we have here? Well, minus 1 volt, pretty much. Multisim is pretty particular about things. Minus 995.537 millivolts, which adds to 1 volt pretty much here, okay? All right. Now, let's do something funny. Okay? Let's just erase those numbers here again. Back to square one. Yeah. Yeah. What if we have 2 volts here? What is that going to give us? Remember, we have the operational amplifier just to show that that thing is there. Okay, that's our amplifier. Rule number 1, no current flows in and out any of the inputs. 2, rule number 2, whatever this voltage is, that is going to be, and whichever one is hardwired, that's going to give us, so this one here is hardwired to 2 volts, so that means this is going to be 2 volts for sure. All right, we can redraw the circuit. We have 2 volts here, and we have 2 volts here. What is the current across the resistor? What is the voltage across this resistor? Well, we have 2 volts here, we have 2 volts here. The voltage across the resistor is 0 volts because 2 minus 2 is 0. What is the current? It's going to be 0 times the value is going to give us 0 amps, which means this is going to give us 0 amps. Okay. What is the voltage drop across the resistor? 0 amps is going to give us 0 voltage drop on this resistor. So that here, since this is 2 volts, we come to here, we go up or down. Now, we go neither way. We stay because there is no voltage drop. This is going to give us 2 volts. Let's check it out. Da-da-deem, da-da-dum. Multisim, stop that here. Let's change that into 2 volts. Press play. Ooh, 2 volts here on the output. Cool, eh? All right. Let's see what we get if we get to the current to flow the other way. Let's make this one again. Yeah, here we have that, and we have that. Okay. Let's make this one 3 volts now, just to be funny. So this here, if we want to keep, if we want to keep the direction of the current, then we're going to have to make sure that the numbers are negative, right? All right. Okay. What is the voltage on this resistor? Well, over here we have 3 volts. And over here we have 2 volts. So the voltage with this direction of the current is going to give us minus 1 volt. It doesn't really matter here because we're interested in the absolute value in order to find out the current. But since we are pointing in this direction, then in this direction is going to be negative current. All right, so what is the value here? So V in over Rn, so calculating the current again, because if we calculate this, we're going to know what this one is. And then we can find out the voltage. Right? So V is minus 1 times Rn. Let's get the calculator. All right, so we're going to have minus 1. All right. What is it? We're dividing it by 10 kilo. And that gives us minus 100 microamps. So let's put that thing here. Minus 0.131. Why do we have this minus? Because this arrow points that way, and in that way the current is negative. The current actually flows that way now because this is higher potential. If this one flows that way, then this one flows that way as well, which is going to make this side of the resistor more positive than that one, and that's going to help us to find out what the output is. So we have that current. Now, that current here is the same times the value of this current, which is 20 kilo. We can quickly do that. That times 20, 1, 2, 3. Boom. That gives us minus 2 volts. Well, let's put it there across this resistor here. All right. Why do we have minus 2 volts across that? Because we have indicated the current flowing that way, and if the current flowing that way, then the voltage is going to be positive, negative here. So we have the voltage pointing that way here. Positive, negative. All right. So what we have here, we have 3 volts here, so we're going to have to change that to 3. Right? And now, what are we going to do? From that, because this is more positive side than that side, we have to count. So we have to add that. So I'm going to change that to plus sign. And what's the voltage? The absolute value, because minus is going to give us plus, and that should give us 5 volts. Cross our fingers. What am I doing here? Let's get the multi-sim. We changed it to 3 volts here, right? We changed that to 3 volts. Okay. Hopefully I didn't make a mistake. Fingers crossed. Whoa, 5 volts. Okay, cool. See? All right. So this is how we analyze using those 2 rules, or the 3 rules, this type of circuits. Let's format that shape again and just get that back here. Over here. I'm going to give you a quiz based on that sheet here. I'm going to ask you to calculate. Here's question number 1. Here's the mysterious amplifier, whatever it is. Here is the value on the output. Here's the value on the input. What is the gain? AV. The gain. AV. All right, so calculate the gain of the circuit. Answer is the gain, voltage gain equals whatever you have to do. All right. Now, question 2, we're going to calculate let's calculate the gain again. But we have this type of circuit. All right. The gain based on this information, what you see, what is the gain here? Calculate the voltage on the output. If you have this type of a circuit, here is the voltage. Here are the resistor values. Let's see what that gain is. And I just to skip the indiscrepancies that would arise due to limitations of the power supply rails, I just said that forget the power supply values. Let's say it's no object. It's connected to plus infinity, negative infinity. What is going to be on the output? And also calculate the voltage on the output with this summing amplifier based on based on what you had. And over here, question 5, power supply rails are plus minus infinity. Calculate voltage out. So we have a different type of, oh, wow. I'm going to give you the quiz, and I'm going to change those values slightly. All right, wait a second. Maybe not. Voltage on this is 3 volts. Here's the 2 volts on the battery. What is the voltage? Just do what we did like a couple minutes ago. Okay. All right. So that's it for the supplementary notes. Well, what did we get? We got some minutes happening here. I'm going to cut that video short a little bit to make it shorter as possible. Okay, that's it. I'll see you in class.